Okay, all right, so we're on the second half of chapter 6, and we've learned how to balance chemical equations. I'm sorry, we've learned how to recognize whether or not chemical equations are balanced. Now we have to actually balance them, right? So I need to be able to give you a chemical equation and you balance it. And so the idea with balancing, here's the key thing that you have to remember, is never misplace your marker.
You got like 8 of them on there.
And here's the one I want. Those are terrible. They don't erase. They're awful.
You need to do whiteboard in here.
That would help. Here's the thing. When you have a chemical equation, I can kind of see the one that was up there previously. There's like a CO2 plus H2O yields C6H12O6 plus. I can't tell what that last one was. Do you guys have it in front of you? What was it?
5O.
Okay, so I'm going to leave off the O2. All right. So this equation is not balanced. In fact, it was actually not balanced whenever we added up all the values in there. But my point is this. If I give you an equation like this and I tell you to balance this equation, you can't touch these little numbers at the bottom. All right? That's not allowed. Because if you touch these numbers at the bottom, you've just changed what that molecule is. All right? Does that make sense to you guys? Like if you had H2O, I can't mess with the 2 and the 1 for the O, right? Because now it's not water anymore. So you can't mess with these little numbers. The only numbers that you can adjust when you're balancing stuff is these numbers in the front, right? You can change those numbers in. Does that make sense? So only the big numbers in the front are allowed. So let's practice an easy one. Let's just see how it works. And this is example 6.3 in the book, and they tell us that hydrogen gas and chlorine gas react to make hydrogen monochloride gas. All right? So they tell us that it's hydrogen, and they tell us it's a gas, and they say that we have chlorine, which is also a gas, and that's reacting together to make hydrogen monochloride, which is also a gas. Now, what's the chemical formula for hydrogen monochloride? How do we know? These are actually the easiest ones because they have prefixes in them. If they have prefixes in them, what kind of compound is it? I think I heard it.
Covalent.
It's covalent, right? Yeah. Look at there. You are famous, dude. You were the first one to get your name on the board on the camera today. Yes. Nice job.
You get a plaque for that.
So it's covalent, right? We only had to use the prefixes in covalent compounds. And so it's super easy to do the covalent compounds. How many hydrogens do I have? I only have one because if there's no prefix on it, we know that it was mono, but if it's on the first one, we don't add the mono, right? We just leave it off. But there's a mono on the second one, so we know that we only have one chlorine atom as well, right? So that's the chemical formula for hydrogen monochloride, all right? So we write this down first of all before we balance it, but are we done? If you guys looked at the problem, you know that I'm missing something else. What else am I missing? Before we balance it, what? These are both homonuclear diatomics, right? We can't put homonuclear diatomics by themselves without putting the little 2 there, all right? So that's something that you're always going to have to check for when you're balancing a chemical equation. If I don't give you the chemical equation and say balance it, if you're just kind of constructing it on your own, you have to check for homonuclear diatomics and put those little 2's next to it. Now, if it's not a homonuclear diatomic, do not put a 2. All right, that's only homonuclear diatomics. And you only have to put the 2 when it's all by itself, right? Hydrogen is a homonuclear diatomic, but it's not by itself here, so it doesn't have to have a 2 on it. It's only when they're by themselves. Does that make sense to everybody? Now, as far as balancing it goes, so we've got the basic equation down. We've taken care of our homonuclear diatomics. We've made sure that our compound is correctly. The chemical formula for this compound is correctly written down. Now I can start messing with the numbers in front if it's not balanced. Sometimes when you write all that stuff down, it's just automatically balanced. But is that the case this time?
No.
It's not, right? We've got 2 H's over here and only 1 H here. We've got 2 Cl's over here and only 1 Cl here, right? So we got to start messing with these numbers in the front here. Yep. she already said the punchline. I hate it when that happens. All right, so 2 right there. So Gracie's right. A 2 in the front there will balance this one. Does everybody see that? Now we have 2 H's here and 2 H's here. 2 CL's here, 2 CL's here. So this one's like super easy. This is like the problem that I'll never give you, right? So it's a little bit too easy. But it's a good one for us to start off with. And what I was going to say, that the key when you're doing this is pick a compound that's, start with an element that's only in one compound on each side. And we'll see what we mean when we do some of the more complicated ones. Sometimes you'll have like oxygen. Several of the ones we do, you'd have 2 compounds over here with oxygen in it. I don't want to start with oxygen if it's in 2 of them, because it's harder to work with those. So start with the ones that there's only one on each. It only shows up in one compound on each side. All right, and that point will be clear as we do some more complicated ones. Any questions about this first attempt? What's the thing we have to remember when we write it down to start with?
You can't mess with the smaller ones, you can only mess with the big
I can only mess with the big numbers in front. We're going to learn in the future those are called stoichiometric coefficients.
For now, they're just the big ones.
For now, they're just the big numbers, right? And you have to check for your homonuclear diatomics, right? Don't forget to do that. All right. Let's try another one. This is example 6.4. And we're told here that sodium bromide and chlorine react to make sodium chloride and bromine. What is the balanced chemical equation? So now our rules, I know you were hoping that the stuff you learned in chapter 4 and the stuff in chapter 5, you could just dump that knowledge and not have to think about it again. Chemistry is not like that. We're going to build with each chapter, right? So you're not going to be able to, usually you're not able to throw stuff away. So we learned how to write the chemical formula for ionic compounds, and we learned how to write the chemical formula for covalent compounds. So when I give you a problem like this, the first thing that you're looking at as you're writing down the compounds is you're going to have to pay attention. Is it ionic or is it covalent? Sodium bromide, ionic or covalent? Ionic, why? Who said that? Josh, why? And we got a metal, right? If it's got a metal in it, it's ionic. And so if it's ionic, we're going to have to swap and drop. All right? We can't dump, swap, and drop. We've got to hold on to that. It's still staying with us. Okay? At this point, hopefully you've done it enough to where it's really simple for you to do. If it's not simple yet, it will be simple by the time we're done with all of this, because you'll have just done it so much. So we've got sodium and we've got bromide. What's the first thing that we have to do before we do the swap and drop piece?
Put their charges.
Put their charges, right? So what's the charge for Na? The metal's always going to be positive.
Positive 1.
It's positive 1 because it's in column 1, right? So it's just a plus. And what about bromine?
7.
It's in column 7A. So that's going to be the negative one, huh? Negative 1. So we start counting backwards for that one, right? So that's the negative 1 and the reason why it's negative 1 is because it's in column 7A, which means it has seven valence electrons and it just wants one more to be ideal, right? That's why we give a negative 1 charge. So Na plus Br minus. And so swap and drop says swap the numbers that are up here and drop them down. Well, the numbers that are up here are both 1s, and so when we drop both of those down, we just have NaBr. Right? So that one was pretty simple. Let's go ahead and we can write down. So sodium bromide plus chlorine. This one's all by itself. What do we have to check and see?
If it's a homonuclear diatomic.
Is it?
Yes.
It is. That's one of our 7, right? Again, something that we can't forget about. Remember, it's hydrogen, nitrogen, and oxygen. And then the first 4 elements in column 7A is what the homonuclear diatomics are, right? So, Yeah. So what? Fluorine, bromine, iodine, and I forgot one. Chlorine, right? The one we just had. So that's a homonuclear diatomic, and then it produces sodium chloride and bromine. Sodium chloride, NaCl. Also ionic, right? Because sodium is a metal. So Na has a plus charge, chlorine has a negative charge, so same kind of thing. It just, when we swap and drop, it just becomes NaCl. All right? So we have NaCl right here, and then that's plus bromine, another homonuclear diatomic. So we put a little 2 there. All right. Now we're ready to balance because we've taken care of all that stuff. We've constructed our individual chemical formulas for each compound, and we can mess with the numbers in front to balance it out. So let's start with something that's, well, we don't have duplicates of any of these here, so we could really start with whatever we wanted to. What do you want to start with? The NAs are obvious because it's right in the front, but are we already balanced on NAs?
Yes.
We are, so what do you want to do instead of NA?
We need to balance BR.
Okay, let's balance BR. So we've got 1 on this side, 2 on this side, so what do we need to do over here?
Put a 2 in front.
Put a 2 in front of this.
Yeah.
Now, when I do that, I have to look and see what else that might have affected. When I put a 2 here, that gave me 2 NAs, so now my NAs aren't balanced. So I'm going to come over here and say, well, I need to put a 2 right here to balance my NAs. So everybody see that? All right, what about chlorine? Well, chlorine's got 2 on this side, but because I just put a 2 here, now I have 2 chlorines on that side. So it looks like I'm balanced. Let's double check. 2 NAs, 2 NAs, 2 BRs, 2 BRs, 2 CLs, 2 CLs, right? If you want to do what I did before where you write them down, if you want to list that out, that helps you, then keep doing that, all right? And in fact, when it gets really complicated, it may be more helpful. But for these basic ones, you can probably just count them in your head. Any questions about how I did that? You guys got that down? All right. Let's see. All right, so let's do one. We've got to get progressively harder, right? What's the point? We just do the same thing over and over. Who wants to do that? Nobody wanted to raise their hand? Let's just stay here. I like these. Let's do one that's a little bit harder. This is going to require some minor math skills. Still not that bad, but we're going to have to use some math skills to balance this one. So let's do, this is example 6.5. There is another one that they have on page 178, 6.4, but I don't know. Let's just see. Let me write it down very quickly. See if we can balance it really quickly. Phosphorus pentachloride. It's phosphorus and pentachloride, so it's got a 5 next to it. They tell us it's solid and liquid water. So a solid plus H2O, which is liquid. I always do that as a cursive L so that you know it's an L, not a 1 or something like that. React to make liquid phosphoric acid, and they give us the formula for that, H3PO4 plus liquid hydrogen monochloride. And so that means there's 1 H and 1 Cl. We had that previously in another. They told us this one was liquid, right? Is that what they said? The first one was liquid? And the second one was liquid?
Yeah.
Is that right? Okay. So let's try to balance this one very quickly. Again, okay, this is the first time we've had one where we've got an element that's in multiple compounds on one side. You see we've got an H in this element and we've got an H in this one. All right, so my recommendation is don't start with H because it affects multiple things if you try to balance the H, and it can just become more complicated. So start with the ones that aren't in multiple compounds on one side. So P is a good place to start, but we don't really have to do anything with the P's because we've got 1 on each side. So let's look at Cl. We've got 5 CLs here, so I'm going to put a 5 in front of this. Right? We're not going to touch the H's yet though because we've got multiple of those, so we're just going to leave that one alone and look at what else we have that's only in one compound, and that would be the O. Okay? So we've got 4 O's here, but we've only got 1 O here. Does everybody see that? So I'm going to put a 4 in front of this so that our O's are balanced. Okay? Everybody followed me so far? Now our P's are still balanced, our CLs are still balanced, and our O's are balanced. So let's count up our H's now. If we look at our H's here, we've got 4 times 2, which is 8, right? And here we've got 3 H's and 5 H's here, which is also 8. So our H's are actually already balanced when we balance the other stuff. So you see why it would have been a mistake to start with the h's? We'd have gotten all kind of wacky numbers, you know. We'd started from the very beginning, we would have made it more complicated than it needed to be. In fact, probably what would have happened if we'd started with the h's is we would have gotten bigger numbers in the front here. And if you do that and you get bigger numbers all the way in the front and they can all be divided by a common factor, then you want to divide through by that common factor and make them as small as possible. Okay? So in other words, like if I had, let's say I started with the h's and it made these numbers get big and I ended up with something like, I end up with something like that, and I notice that all of the big numbers in front are divisible by 5. Then divide through by that 5, so you can make it as simple as possible, and that will give you this here. Okay? Alright. Because technically this isn't wrong. Like this would give you this chemical equation, but when we're writing the chemical equation, we need to make it as simple as possible, and so we would want to write that one down for it to actually be correct. All right, questions about that? Good, now we'll go to 6.5. And I would encourage you to not look at the answer and just try to think through this, because this is one where students start really getting confused with it. And I think if you kind of try to think through it with me, then it'll be clearer than trying to process what's in the book and listen to what I'm saying. So a pocket lighter generally burns butane. Butane, they tell us, is C4H10. And in the reaction, butane reacts with oxygen in the air to make carbon dioxide and water. So it's combined together with oxygen to make carbon dioxide plus water. All right? Is that formula correct?
No.
Why? I mean, not balanced, but is the basic formula correct?
Maybe.
Anybody want to definitively say yes or no? You're saying no, Sayu, or you're saying you don't want to say?
I'm saying no.
Sayu's saying no. Okay, that's right. Sayu's correct. Why, Sayu?
You're missing a 2 in front of them.
We've got O by itself, and it's a homonuclear diatomic, so we have to put a 2 there, right? If this, for example, had been C, we would have been done, because C is not a homonuclear diatomic, so we would put the 2 there, right? So don't forget to look for your homonuclear diatomics. All right, so now let's balance this guy. What do we not want to start with?
The H's.
H's are fine. They're only in one compound on each side.
Oh.
The O's, right? The O's are the more complicated ones, because we've got O and 2 compounds over here. All right, so don't start with those. So let's start with, just because C comes first, let's start with the C's. I got 4 C's here, so what do I need to put in front of this? 4 to balance my C's. I've got 10 H's here, so what do I need to put in front of this to balance my H's? 5, all right? So now let's take a look at our O's. I have 2 right here. What do I have on this side? 4 times 2 is 8, plus another, how many in this one? Another 5, so 8 plus 5 is 13. You guys see that? So I have 2 O's on this side, I've got 13 O's on this side. Is there a number I can put in front of this right here to give me 13 O's?
Can you use a decimal?
Oh, don't think about it like a decimal, think about it like a fraction. What fraction could I put in front of this? I mean, and if you want to, if it's easier for you to think in decimal terms and then you convert it to a fraction, that's fine. Yep.
Is it 13 divided by 2?
13 divided by 2, right? So if you want to get, if everything else is balanced and you just got this one problem child, right? We all do. You understand that, Josh. Joshes are generally problem children, right? So if you, have I put your name on the board yet? If I pick on you, I definitely want to give you some pity points. So if there's one problem element or compound in the equation, and that's the only thing that's causing an issue, and you can't put a whole number in front of it, then see if there's a fraction you could put in front of it and your equation be balanced. Does everybody see that if this equation was allowed, do you see that we would be balanced now? Because this would give us 13 right here, right? Now, if you're not great with fractions, all right, really, really easy, whatever number is here, all right, just put the number that you want to get on top, which in our case was 13, and then put the same number on the bottom that's right here next to it. So if this had been 03, we would have written 13 thirds instead of 13 halves. Okay? Does that make sense to everybody? But everybody needs to see that 13 halves times 2, when you do that, the 2's cancel out and we're left with 13. Alright, so now our equation is balanced. The problem is, we can't have 13 halves oxygen molecules. This 13 halves is the same as 6.5, right? So we can't have 6 oxygen molecules and then a half of an oxygen molecule. That's not allowed. How do I get rid of this? I get rid of this 13 halves by thinking about this as an algebraic equation. If this was an algebraic equation and I wanted to get rid of the fractions in there, what would I do? I would, you said multiply by the reciprocal. No, I'm just trying to get rid of the fractions. I'm not trying to, when I say get rid of the fractions, I'm not trying to say that I want to totally get rid of this value here. Because if I multiply it by the reciprocal, then I'm going to end up getting fractions in front of my other things. I want to make sure there are no fractions in the problem. What's the solution?
Don't you just like multiply everything by
By 2.
the greatest common denominator or least common denominator?
Yeah, I never can remember either. But yeah, you want to multiply it by something that's going to get rid of all of your denominators. In this case, it's easy because we've only got one fraction, and I will just tell you all of the problems that I'm going to give you, it's going to be easy like that, right? You'll have the same denominator if you have multiple fractions, but usually it'll be like that. So you'll just have a fraction in front of one, and so we want to multiply through by 2 to get rid of that, right? But since we're thinking about it like an algebraic equation, we have to multiply both sides by 2. Every compound that's in there, we've got to multiply by 2, okay? So that's going to give us 2C4H10 plus 13 halves times 2 is just 13, all right? 13, O2, plus 2 times 4 is 8 CO2, plus 2 times 5 is 10 H2O. And now if we count it all up, we'll see that we've got a balanced chemical equation, okay? So don't be afraid of having bigger numbers after you do that. Sometimes those numbers get pretty large. But if you did it correctly, you will see at the very end, we don't have a common factor that we can divide all these by, right? There's no way to make it any simpler than it is. All right, any questions about that? That's as complicated as it gets with balancing chemical equations in here. So if you can do that, you'll be good. All right? Bless you. So what we want to spend the rest of our time doing today is constructing some special types of chemical equations. All right? You need to be familiar with what these are. And so if I tell you, give me this chemical equation, you should be able to do it. And the first is a formation reaction. So a formation reaction is one where 2 or more elements react to form, right? That's our key word there, formation. So we're forming something to form a single compound. Okay? So the flip side of this, so like in the case of a formation reaction, we're always going to have what on this side? On the right side, on the product side, if it's a formation reaction. So if I said, for example, give me a chemical equation for the formation of carbon dioxide. So somewhere carbon dioxide is supposed to go. Where's it supposed to go? On the left or the right side of the chemical equation? The right side, because we're forming it, right? And it goes over here all by itself. So if I'm saying, give me the chemical equation for carbon dioxide, it has to go over there, right? If it's a formation reaction, you'll always have just one thing over here. Whatever the thing is that you're forming goes over here by itself, all right? And then on the left side, we put down whatever it is that makes up that thing. So in this case, it's just got C and O in it. So we'll just have C and O on the left side. Now when we do this, when we put individual elements here, what do we have to look for?
Homonuclear
Homonuclear diatomics, right? We've got that. Is C homonuclear diatomic?
No.
It's not, so we leave the 2 off of that. And then when we check it, we're balanced. This is the balanced formation reaction for carbon dioxide. Okay? See how easy that is? Now the opposite of that is what we call a decomposition reaction. So think of something decomposing, right? It breaks down. So for this reaction, we're going to start with something all by itself on the left side, and then we're going to break it down into its individual pieces on the right side. All right? So it's the reverse of a formation reaction. So a decomposition reaction has only a single compound as the reactant. What do I mean when I say reactant? We're talking about chemical equations.
The left side.
The left side, that's the reactants, and the products are on the right side, right? So a decomposition reaction has only a single compound as the reactant, and the products are the elements from which the compound is made. All right, so let's say, for example, I want you to give me the decomposition reaction for water. What am I writing down?
H2O.
H2O, okay. Then what?
Then the arrow.
The arrow, right? This has to be all by itself on this side because it's decomposing.
Into H2 plus O2.
H2 plus O2. So she was mindful of her homonuclear diatomics, right? And she made sure she included every element that was in here. So that is the decomposition reaction. What's the only thing left to do? Make sure that it is balanced, right? So is this one balanced?
No.
It's not, because we've got 2 O's here and only 1 O here. So we put a 2 in front of that. Now the H's are in balance. That's not a big deal. We can put a 2 there. And so now we're balanced. Everybody see that? Cool. All right, questions about decomposition and formation reaction?
So just know how to be able to do something like this if he gives us a question like that on the quiz.
Yep. And know how to recognize it. Like if I gave you guys one of these and I asked you what kind of reaction is it, you should be able to tell me this is formation because it's just one thing over here by itself. And the individual parts over here. And the flip of it, right? All right. I want to make sure we have time to get to the last type of reaction, which is pretty important. So I'm going to keep moving along rather than doing the 2 examples in the book because I think you guys have this one down. Just realize that sometimes you may have more than just 2 things in it, right? Like one of the examples they have in the book is CaCO3. And so they said, what's the decomposition reaction for that? So just to make sure that you guys are clear before you balance it, what's going to go on this side? It's a decomposition reaction, so we know this is over here all by itself.
So it would be Ca
So on this side we have to have Ca plus
plus C
plus C plus
plus O3.
Not O3.
No, no.
It's a homonuclear diatomic, so if it's by itself, it's just O2, right? Yeah, I'm glad we did that, because I don't want you to grab what's here and say you just move that directly over, right? The reason, if this had been like, for example, a Cl, and we put Cl right here, we'd had to put a 2 on it, because it's a homonuclear diatomic, right? These are not, so we just put those as they are, but the O we have to put a 2 on. And then we look at it and we balance it, right? So we might as well do it since we've already written it up here. We've got 2 O's over there, and we've got 3 O's here. This is actually a good one because it's the first time we've had to do this type of thing in our balancing. What am I going to do about that? Gracie?
You put a 2 in front of the CaCO3, and then you would have to put the 2 in front of Ca, 2 in front of C, and then a 3 in front of.
Yeah, so if I'm just focusing on the O's, because the O's that were the ones that were out of whack, if I put a 2 here, I can put a 3 here to give me 6 on both sides, right? And then I just need to go back and revisit the CA's and the C's, and so, like Gracie said, a 2 here and a 2 here will take care of that, and we're balanced, okay? We could have done the trick also where we did the fraction, right? Let's just think about that real quick. How would I have used the fractional solution to do that? I had 3 O's here, and I had 2 O's here, but I want to have 3 O's here. So does everybody see I could have then put a 3 halves in front of that? But then I got to get rid of the fraction, so I multiply everything through by 2, right? I'm just going to put a big 2 around the outside here. And so then when I do that, I get the same thing that we had before, right? 2Ca plus 2C plus 3O2. So I would have gotten the same thing if I'd used the fractional solution as well. All right? These next reactions, I'm not going to ask you to build these from scratch, but I want you to be able to recognize these. All right? So let me just draw 2 of them on the board to make sure you can recognize it. And they are this one here, zinc, solid zinc plus copper sulfate in aqueous form. What does aqueous mean? You guys remember? I think we talked about this. It's been dissolved in water, right? So it's this substance here, but dissolved in water. So this may have started off as a solid, but we dissolved it in some amount of water to make an aqueous solution. Plus solid copper plus zinc sulfate, which looks like this. All right, so that's our first reaction. The second reaction that I want to show you is potassium sulfate plus calcium chloride. Oh, wait a minute, let me check on that. Yeah, that's right. Calcium is a metal, so that's one of those weird ones that I never can remember. It's like it's not obvious to me that it's a metal. But I thought it was. Calcium chloride yields calcium sulfate in solid form plus 2 potassium chlorides in aqueous form. All right, so this is what you need to see, what you need to recognize with these 2 reactions. So that if I gave you these reactions and said, what kind of reaction is this? This is what you're paying attention to. That should make it kind of obvious. We know it's not decomposition or formation. Why?
Because they both have 2.
They have 2 on each side, right? We got to have only one thing on one side if it's going to be decomposition or formation. So we know it's not either of those. Notice what happens right here. We've got zinc plus this copper atom, and this copper atom is in a compound with this SO4, which we're going to learn is sulfate. Later on, it's what we call a polyatomic ion. So we learned about ions, but sometimes ions can be constructed of more than just one element. So that's what that is. But the point is, we've got Cu linked together with SO4 here, but when we go to the other side, you guys see how the zinc has jumped in and replaced the Cu, and now we have ZnSO4, right? So what was the thing that was in the compound here turns out to be the other thing in the compound here. And so what we refer to that as is single displacement. So this is a single displacement reaction, all right? Because the zinc displaced the copper when the reaction took place, all right? So that's a single displacement reaction. Now we've got something very similar going on in the second reaction. Does everybody see that the K2 is combined with the SO4 here, but on the other side of the equation, the Ca is combined with the SO4. But unlike this one here, where the Cu was in here, but then it's by itself over here, the K2 isn't just hanging out by itself on the other side. It's actually joined together with the Cl, which is what the Ca was linked with over here. All right. So what happened in this reaction is the two basically swapped places in the compounds. Do you guys see that? All right. So we call that a double displacement reaction.
So it's either going to be single or double displacement?
That's right.
Okay.
Yep. So if you have two compounds on each side and you have some elements that swapped places, then it's double displacement. This one though, this isn't a compound, right? This is just zinc all by itself. So we don't have that scenario where they're swapping places in two different compounds. So that one's a single displacement. All right, any questions about that? We're doing good. We got about 15 minutes to spend on what is arguably the most important reaction that we're going to talk about in this section here. The most important type of reaction.
Complete combustion.
Complete combustion, or just combustion in general. Combustion reactions are very important and used over and over again in chemistry. So we got to make sure that we understand this. And a combustion reaction, you write down the definition. Combustion reaction. What do you think of when you hear combustion?
Like engines?
Fire.
Engines. What's going on inside the engine when combustion takes place? There's something that we have in our automobiles when that combustion is happening that has to be there in order for the combustion to work. What is it that we have to have? Spark plugs. There has to be a spark, in other words, right? So combustion reactions involve something burning. All right, there's got to be fire when there's combustion reaction. And from what you guys did, probably way back when in physical science or whatever, you probably have done an experiment somewhere where you lit a candle and you took a glass jar and you put it over the candle. And what ended up happening when you did that? The candle goes out. Why does the candle go out?
There's no more oxygen.
All the oxygen is used up, right? So in other words, for a combustion reaction, in order to have flame, in order to have a combustion reaction, you have to have oxygen, all right? So that's what's happening with combustion reactions. We're taking some compound and we're combining it with oxygen, all right? So a complete combustion, a combustion reaction is the process by which a chemical reacts with oxygen to form one or more products as well as heat and usually light as well. Now, within the discussion of combustion reactions, there's two different types that we want to talk about. And the first type is complete combustion. And complete combustion only produces CO2 and H2O. There are some cases where you'll only make one of these, and we would still consider it to be complete combustion, but for the purpose of this class, all right, we think of complete combustion as the only products, the only thing that we're going to have on the product side of our equation is just CO2 and H2O. Okay? So for example, if we had something like this, 2C8H18 in liquid form plus 25O2, that's a, and try to separate that 25 and that O so it doesn't look like a zero. 25O2 in gas form, plus, not plus, yields 16CO2 in gas form and H2O in gas form. That right there is what we would call a complete combustion reaction. Now, how do I distinguish this from, for example, how do I know it's not formation or decomposition? Again, because there's not a single compound on one side or the other. How do I know it's not single or double displacement? Well, we don't have this, like if it was, it couldn't be double displacement, but it could be single if this oxygen jumped in here and like replaced the C or the H, and that's all that happened. That's not all that happened, right? We have CO2, we have H2O on the other side. So basically, anytime you're seeing a single compound and it's combined with oxygen, you know it's a combustion reaction. All right? And if what you see on the other side is only CO2 and H2O, then you know it's a complete combustion reaction. Does that make sense to everybody? This is what we want to happen when we're burning stuff. We want complete combustion to be what you experience. We don't typically think of H2O. We don't think of water as being something that happens as a result of burning something, do we?
So when you go into like building engines, you look at the complete combustion in the terms of the spark plugs development, or
You want that to happen.
yeah.
You want it to be complete combustion. The reality is that you're going to produce carbon monoxide, which is what we don't want because it's poisonous, right? And that's a good segue into our next type of combustion, incomplete combustion.
What scenario would you want in complete combustion?
I mean, if for some reason you needed carbon dioxide, then sure, right? If that's what the goal is, right? If you're making poisonous gas to use for whatever reason, right? Maybe in warfare, we want incomplete combustion reactions because we're trying to make carbon monoxide bombs. I don't know, you know?
So, one's for car engine, one's for gas.
But, so this is a combustion reaction. Incomplete combustion is a combustion reaction where you get CO or just plain old carbon, elemental carbon, instead of CO2. Now, if you look at that, what's different about CO and C, if that's what we end up getting? What do they have less of than CO2 does? They have less oxygen, right? And so typically what happens in incomplete combustion reactions, there's a lack of oxygen. There's not enough oxygen to fully react with whatever the chemical is that we're burning, okay? And so this is why you should have a carbon monoxide detector in your home if you have natural gas in your house or if you have a fireplace in your house, right? Because if you're not getting enough oxygen in there, like in the case of a fireplace, if you're not getting enough airflow, then you could be producing carbon monoxide because you're creating incomplete combustion instead of complete combustion.
Don't they have those in planes too?
Carbon monoxide monitors?
I'm not sure.
I mean, it would surprise me.
I'm pretty sure, yeah.
Yeah. I don't know the details as far as how that, what all's going on inside there. It might not even be related specifically to the engine. It could be related to, you know, just whatever's
Just the cabin.
creating the air and all the stuff in the cabin, you know, keeping the cabin warm.
That's what I was.
But yeah, that makes sense. They're having to heat it some way, right?
Yeah, that's what I was thinking, if we have one, need to check it before you know.
Yeah. So I mean, we have a carbon monoxide detector right next to our fireplace for this reason, right? And with fireplaces, one of the ways that that will sort of evidence just visibly that you may have a lot of incomplete combustion is if you have an excess of soot, right? If you have a lot of soot in your fireplace, you're getting a bunch of elemental carbon. So if it's really nasty and you're having to clean it all the time, there's a good chance you don't have good airflow. And so if there's not good airflow, you're increasing the chance. Elemental carbon's not going to hurt you, the CO will. So there's a higher risk of carbon monoxide production.
So do you just get your vents fixed in that case? Like what would you do to fix the issue?
Yeah, I mean, you could have an issue because maybe your chimney's clogged, because that airflow is like kind of coming, you know, from inside your home through your chimney, right? And so if you're not, for whatever reason, if your chimney's stopped up and you're getting the backup of that movement of oxygen, then it could be something that probably just needs to be cleaned, you know? But yeah, that's something to keep an eye on if you use your fireplace a lot. All right, does that make sense though? So here's what I will typically give you. I will either give you something like this and you have to recognize what type of reaction it is. So if I gave you this reaction here, you should be able to tell me it's complete combustion. But if I gave you this reaction and it looked like this instead, then you should be able to tell me it's incomplete combustion, right? Because we don't have CO2 and H2O. But more commonly, probably what I'm going to give you is I'm going to actually tell you, write down the chemical equation for the complete combustion of something. All right, so let's try one of those, and that will be our last example for today. And so it says, what is the chemical equation for the complete combustion of liquid ethanol? And they give us the formula for that, C2H6O. So C2H6O is liquid ethanol. And that's all they need to give us to build the complete combustion reaction. We should be able to do the rest. So if it's complete combustion, what am I combining that with? Oxygen in the air, right? So that's always going to be O2 in gas form. Now, it's great if you know what the phase is to write that down. I'm not going to count that wrong. All right, so I don't want you guys stressing over the correct phase, unless the problem asks you for that explicitly. But most of the time, if we know it, write it down. We should write it down to be as accurate as possible. But if you don't write it down, if I say complete combustion and you didn't write down the phases, I'm not going to count off for that. Okay? So O2, what am I having on this side since it's complete combustion? Did you give me that, Aaron? Were you the one that said that? Okay, so what's on the right side? Can you tell me that?
CO2.
You're not supposed to look, man. Come on, dude. So it's complete combustion. So complete combustion only produces CO2 and H2O, right? So CO2 in gas form plus H2O. We don't typically see water, I wrote down liquid. We don't typically see water running off of our fires, right? So the H2O is in gas form as well. So that's the basic reaction. If I ask you to do a complete combustion reaction and you write that much of it down, I'm going to give you at least half credit for the problem because you understood what complete combustion was, but you're not done with the problem. Why?
It's not balanced.
We got to make sure it's balanced, right? It could be, but we have to check it. And in this case, you're right, it's not. So again, we're going to start with something easy. What do we not want to start with?
The
Don't start with the oxygens, right? Because it's all over the place. I said every single compound here. So let's start with the C's. I have two C's here. I've only got one here, so I'm going to put a big 2 there. Next, we'll look at the H's. I've got 6 H's here. I've only got 2 H's here, so I'm going to put a big 3 there. And now I count up my O's. I have 1 and 3 on this side. I have 4 and 7. I'm 4 and 3 on this side, so I've got 7 on this side. So for my O's, I've got 3, and over here, I've got 7. So I've got a deficit of 4 O's, right? I need some more O's. So how am I going to get 4 more O's? Yep.
You put a 3 in front of O2.
Yep.
6 plus
So if I did that, now I've got 1 plus 6, right? 1 plus 6, and that's going to give me my 7. We didn't touch anything over there. Putting the 3 here didn't affect anything else. So that's all we need to do on this one. So it's balanced. Right? All right, any questions about any of that?
So for the test, just know like the singular, double, and
Be able to recognize that.
Yeah, and the formation and decomposition. So just know those 3, one or the other. So those equations next to it.
Well, there's as far as recognizing, you need to be able to recognize complete combustion.
Yeah, very complete.
There's 6 altogether.
Yeah,
You got to recognize, right? But the only ones that I'm going to ask you to do are just formation, decomposition, and complete combustion. Okay? All right. Cool. Go have a good day.